This is going to be a quick review of some common math that we're going to use in microeconomics. Twofold. Number one, just so that there's a common place where we do some introduction to some of the basics. And number two, to allay any fears about this class needing too much math. We are going to use some math, but hopefully you'll see at the end of this little short review that it's not too much. So number one, we start with variables, right? So economists love trying to thinking about different pieces of information in the world, right? There's these underlying pieces of information that sometimes we can easily observe and sometimes we can't, right? We can very easily count up the number of trees in a certain area. That's a pretty easy metric that is easy to verify by an outside source. And other times, if we're thinking about something of like your level of happiness with a given purchase, that might be a little bit more difficult thing to measure, right? But economists are always trying to come up with different variables to try to measure some underlying piece of information. And oftentimes we want to think about not just a variable, but rather a relationship between variables. And so we're going to introduce some terminology here, right? So we've got the term on the left, direct relationship, is the terms that we're going to use when we talk about two variables that move in the same direction. Sometimes this is also referred to as a positive relationship between variables. It just simply means that their direction of change is going in the same direction. They're either both increasing at the same time or both decreasing at the same time. And I've got a picture of temperature and the amount of sweat that someone does. And you could think about temperature. We've got some pretty standard ways that we could measure how much temperature there is, what the temperature is. Can you think for a second about some of the different ways that we could try to measure how much someone sweats? There's actually a lot of different ways that we could try to operationalize that concept of how much someone sweats in different ways that we could try to measure it, right? But I think it's pretty reasonable to say that there's probably a direct relationship between those two, right? That it tends to be when we would see this is all about the change in a variable, right? So I'm using the same symbol delta there for change. When the change in the temperature is positive, when the temperature is going up, we often would see a change in the amount of sweat that someone does also increasing. That movement is in the positive direction. That's what we're saying by a positive or direct relationship. At this point, though, we're not sure if this is a causal relationship or if it's just a correlation. That's okay. We're just introducing some terminology here, right? Direct relationship. How about an indirect relationship? An indirect relationship is the opposite. It's when variables move in the opposite direction, or sometimes this is referred to as an inverse relationship, or sometimes it's known as a negative relationship. That's saying that when one of the variables increases, the other variable decreases, right? They tend to move in opposite directions. And so I've got a picture here of some alcohol and a student studying and that's supposed to represent your performance in a semester, right? And so we think that there could be a reason that we might observe an inverse relationship between these two variables. That means, right, that when the amount of alcohol consumption goes up, it's possible that we could see a decrease in your performance in a class, right? That moving in opposite directions, that's what we'd refer to as that inverse relationship between these two variables. And so the third category is just when there's no relationship, right? And I've got a picture of me and a picture of, again, your class performance with the idea about whether I feel good about you or bad about you should have no impact on my evaluation of your class performance, right? That there's no change in the evaluation of your class performance based on whether my approval of you goes up or down. My personal feelings, right? My personal feelings going up or down, right? So again, this is mostly just some terminology that we're going to use throughout this class. More useful, we're going to do a ton of graphing in this class, and so we wanted to talk a little bit about some basics of graphing. Again, you probably recognize something like this, y equals 40 plus 5x. You probably remember from an earlier class that has the classic y equals mx plus b format, right? And so if we want to graph this thing out, we can talk through that. On the right, I've got a little graph. The very first thing I do with every graph, got to make sure that I have my label on the axes. So traditionally, what we measure is horizontally x with the y equals mx plus b. But more generally, right, the variables that are on the right-hand side, those are the ones that we tend to put horizontally, right? So we refer to those as the dependent or the independent variables. On the right-hand side, those are the independent variables, right? And then vertically, let's measure that as y, because again, that's the variable that's on the left-hand side. That's where we put what we call the dependent variable. So in this classic y equals mx plus b format, we have two parameters there. We've got a b and an m. That b, if you recall, represents the intercept. Specifically, it's the vertical intercept, right? So the vertical intercept in this equation is the constant term. It looks like from the numbers, that's the number 40. So again, I'm measuring y vertically. Let's put a little dash there and mark that as 40. What does that mean though, right? So what we can say is this vertical intercept represents the value of y when x takes on a value of 0. Mathematically, we can take this equation, y equals 40 plus 5x, oops, that's a 5x, right? And if I just plug in the information that I have, x takes on a value of 0, I can use the equation to solve for y. When x was set equal to 0, y took on a value of 40. That's what this point on the graph represents. X, the thing that I'm measuring horizontally, is value at 0, and y, the thing that I'm measuring horizontally, is taking on a value of 40. That's the point that corresponds to this thing that I call the vertical intercept. More generally, the vertical intercept represents the amount of our dependent variable when we have 0 for our independent variable, right? And sometimes that's a useful piece of information, and sometimes it's not. Sometimes that doesn't associate with anything in the real world. Okay, so we've got the b that we talked about. The other parameter we talk about is the m, the slope. So if you recall from an earlier class where you learned basic algebra graphing, m, the slope, is equal to the rise over the run, right? Or the change in the thing that I'm measuring vertically divided by the change in the thing I'm measuring horizontally. In this case, the change in y divided by the change in x. So here we go. Two things. Number one, I can just look at this equation and I see that the slope is plus 5, right? So because it is a positive number, plus 5, not a negative number, what I know is that this line is going to have an upward slope to it. Specifically, that 5 tells me how steep the line is, right? And the other thing that I know is that in a classic linear equation like y equals mx plus b, it's not just going to be an upward sloping line, but it's going to be a straight upward sloping line. So let me grab this straight line, boom, something like that. Right, totally could be the graph of this equation. It's a nice straight line, starts at a vertical intercept of 40. So what does that slope of 5 represent? Here we go. Let's use a little bit more algebra on my earlier equation. So we already did the calculation. When x took on a value of 0, we got a value of y that was equal to 40. What if x takes on a value of 1? Can we pull through this that value through the equation again? So I've got 40 plus 5 times 1, y equals, that's 40 plus 5, y equals 45. So again, what was it? When x took on a value of 1, y took on a value of 45. So here's the thing. I want to pick both of these two calculations together. When x went from a value of 0 up to 1, y went from a value of 40 up to 45, right? That's the change that I'm talking about with the slope, right? Except the way that we calculate the slope, it's the change in the thing I'm measuring vertically, which in this case is y. Y went from 40 up to 45, so I calculate that change by 45 minus 40, divided by the change in the thing I'm measuring horizontally. In this case, the change in x. X went from 0 up to 1, so I calculate that change by 1 minus 0. And if I do that math, 45 minus 40 is 5. 1 minus 0 is 1. The slope was positive 5. It represents, right, again, more generally, the slope represents when I have a 1 unit increase in the thing I'm measuring horizontally, it's how much the thing I'm measuring vertically is going to change by. When x increased by 1 from 0 to 1, y changed by 5. It went up by 5 to 45. The slope was the change in 5 vertically divided by the change in 1 horizontally. And notice, when this is a straight line, it doesn't matter whether I'm picking 2 points that are next to each other or whether I pick a point that's 10 units away, right? It's a straight line, so that ratio of the change vertically divided by the change horizontally is always going to be constant. So part of what I don't like about this equation is that it just considers y's and x's, and I have no idea what that represents. Most of the time in this class, what instead we're going to be considering is a graph or a model of something a little bit more specific. So I've got a graph here, or a model here. There's a couple of different ways I can use this language, right? To the right, I'm going to make a graph, but that graph really represents a model. To the left, I've got an equation, but that equation also represents that model. So my model is what? What's my dependent variable on the left-hand side? That's grade, right? We're saying that grade is a function of, grade depends on the value of, what am I measuring on the right? Hours of study. So let's make our life easy and do G for grade and H for hours of studying, right? So if you notice, this is a nice little simple linear form of our grade equation. We've got grade, G, equals 40 plus 5h. That still has the same traditional y equals mx plus b format to it, but I don't have a y and I don't have an x. But everything that we just talked through still is going to follow through with this basic linear model, right? Instead of y, I have g. So when I graph this thing out, instead of having y on my vertical axis, that's where I'm going to be measuring grade. Horizontally, right, in the last one we were measuring x, but now we don't have x. Instead, as our independent variable, we have h, the amount of hours of studying. But notice that when I think about the intercept and the slope, those numbers look familiar, don't they? The vertical intercept represents the level of g when h equals 0. Can I do that calculation real quick? So if h takes on a value of 0, then my g equation becomes 40 plus 5h, oh, not h, 5 times 0, and my g equals 40. So again, when h takes on a value of 0, g takes on a value of 40. What does that point represent? That's saying that's the amount of grade when you don't study at all, right? When hours of studying equals 0, it's your grade. This is probably more of an average grade than a perfect prediction for everyone in the class, right? So is that a reasonable assumption? Right? We alluded to this in the topic material earlier, but every model is based on a set of assumptions. One of the assumptions that we just highlighted with our graph was that this model assumes if you don't study at all, your grade is going to be equal to a 40. Do you think that's a reasonable assumption? Do you think there's a way that we could maybe look at some data to find out whether that assumption was valid or not? Okay, so we've got the intercept, now the slope. Well, notice the slope here, again, to find the slope, all you have to do in a simple linear equation is just look at whatever that number is in front of your right-hand variable. Whatever the coefficient is on your independent variable on your right-hand side. In this case, again, it's plus 5. It's plus 5, so I know, because it's a positive number, that it's an upward sloping line. So I can go ahead and do it just like I did before. And actually, right, if I think about that, doesn't that graph look just like the graph earlier? The only difference is, instead of talking about x's and y's, now we've got a story that we can tell about the amount someone studies and what their grade is. What does the, all right, so we already did this calculation of what is the grade when h equals 0. Your grade equals 40. And if you verify for yourself that when h takes on a value of 1, g is going to have a value of 45, right? What's that saying? That's saying that going from 0 to 1 hours of studying, or said differently, for your first hour of studying, what happens to your grade? Your grade goes up by 5 points. But now real quick, can we do this math? Pause for a second and make sure that you can carry this math out. I'm going to jump right to the equations. or right to the final answer, when h equals 0, g equals 90. And when h equals 11, g equals 95. Where are those points on the graph? Right, so h is probably, I'm not doing an exact measurement here, but h at 10 probably somewhere around there, right? You study for 10 hours, your grade's a 90. You study for an 11th hour, and my goodness, what happens to your grade? It goes up by 5 points. Pause for a second, because that's another really important assumption in our linear model. Notice what happened when you studied your very, very first hour. What happened to your grade? It went up by 5 points. When you were already studying for 10 hours, that sounds like a lot of studying. When you were already studying for 10 hours and you study one more hour, your grade went up by another 5 points. One of the assumptions of a linear model is that it doesn't matter how long you've been studying, every single additional hour that you study, your grade is always going to go up by 5 points. So I step back and I say again, that's an assumption that's built into our model. Do you think that's a reasonable assumption? Does that match what your intuition tells you about having been a student for a good chunk of your life, that every single hour of studying always produces the same effect on your grade? I think there's some really good reasons to believe that this grade function is an oversimplification, right? I think if we wanted to have, I'm going to do this in blue, a more realistic grade model, I think it might look something like this. And it might even, oops, that wasn't supposed to, that's a nice little line. And it might even start ticking down there right at the end, right? I think that that line in blue is probably a little bit better representation of the real world, in the real world, how the relationship between hours of studying and your grade actually looks like. But here's a question. That line in blue, how many of you would feel comfortable coming up with an equation to describe that line? Right? This simple little linear model that we did, it's probably incorrect. But mathematically, it's a lot simpler for us to understand what's going on. So there's this trade-off here between complexity and our ability to trace out the mathematics. We get a little bit less complex, but we can follow through the math a little bit easier. Sometimes we're willing to make those trade-offs with having less sophistication, less complexity in our models if it means that the mathematics is a little bit easier for us to deal with. So again, just wanted to point out a few assumptions. I'm going to take all that away because there's one other thing that I wanted to do here. We've been talking implicitly about the story of when my independent variable, when the thing I'm measuring horizontally, giving a value of the thing horizontally, calculating what the value of my dependent variable was, right? The thing that I'm measuring vertically. I gave you a value of h, and we calculated the value of g. Can we go the other direction? Instead, if we knew the value of g, could we find out from the model what the value of h was? That's exactly what this question down here is asking. What's the hours needed for a grade of 80? We do this the same way that we did earlier, right? Notice earlier what we did is we knew one of the variables, in this case h. Here we know one of the variables, but in this case what we know is that g equals 80. Earlier what we were trying to do is we were trying to find the value of g that we didn't know. Now we're trying to find the value of h that we don't know. What's the value of h that's going to make g take on a value of 80? Actually, we do the exact same process that we were doing earlier, right? What we did earlier is we plugged in the information that we knew. In this case, my equation is, again, g equals 40 plus 5h, right? But now, what's the information I know? The information I know is g equals 80. So let's plug that in. And what I do not know is my value of h. So that's still an unknown. I leave that as the variable. Now I just need to do a little bit of algebra to solve for that value of h, right? So if I pull this 40 to the left-hand side, I'm going to be left with 40 equals 5h. So if I divide both sides of my equation by 5, then cancels out on the right-hand side, and I'm left with h equals 8. And again, this answers my question. How many hours would I need in order to get a grade of 80, I would need 8 hours according to this model. Right, so, and again, just the big conceptual thing is, right, all we're doing is instead of plugging into the right-hand side, we're plugging what we know into the left-hand side. That's what we do to go the other direction. If we know the thing we're measuring vertically and want to find out the value of what we're measuring horizontally. The last mathematical thing that we're going to do, percentage changes. We're going to calculate a few percentage changes in here, and so we just want to make sure that everyone's on board with how to do this, right? So a quick little example. Let's assume that we've got inventories of apples for year 1 and year 2, right? So in year 1, 20 apples. Year 2, 23 apples. What's the percent change in the amount of apples that we have? So some notation. Percent, and again, that triangle for the Greek symbol delta to represent change. The percent change, that's going to be my shorthand notation for percent change. Let's turn this into some notation that's going to be useful to use, right? So I've got apples in year 1 and apples in year 2, those are A's. The way that we would calculate the percent change in apples, the percent change in apples would be A2 minus A1 divided by A1. This is the general setup of how we calculate any percent change, right? In the numerator of this thing, what we have is the ending value minus the initial starting value, and then in the denominator we divide by the value that we started out with, our initial starting value. So to carry out this math, percent change in apples, let's see, that's 23 minus 20 divided by, my starting value is 20, which is 3 over 20, which is 0.15. And if you want, you can multiply by 100. And in fact, when I do percentages later in this class, I am going to do this as well, because that, many of you are going to see the 0.15 and know, that's 15%. But if you multiply it by 100 and slap a percent sign on it, that's the way that makes it a little bit more obvious when we actually use that percentage notation. So we do, right, we are going to make that adjustment of multiply by 100. It's a 15% increase, right? Real quick, what if we calculated, or what if in year 3, we went down again to 20 apples? Could you calculate the percent change? From year 2 to year 3, right, we'd be going from 23 down to 20. Does that mean that it's a negative 15%? Think about that, right? So my numerator is going to change, but this denominator, right? When we're calculating from year 2 to year 3, that value that would go in my denominator, it wouldn't be 20 anymore, it would be the 23. And so the direction of change between variables, it matters, right? And so it matters in terms of calculating the exact percent change. So we're going to practice with this as we get to the application parts of this class, but we wanted to make sure that we laid out a simple little explanation of some of the math that we are going to use.